That because these bursts mark the deaths of massive stars, an unusually dense cluster of bursts in one region of sky should indicate an unusually dense cluster of galaxies behind them. That method revealed the Hercules Corona Borealis Great Wall, a colossal, loosely connected filament of galaxy clusters spanning an estimated 10 billion light-years, more than 1/10 the width of the entire observable universe, making it, by some measurements, the single largest structure ever identified in the cosmos, so large that a beam of light would need longer to cross it than our entire solar system has existed, though its exact boundaries and even its status as a genuinely bound structure remain a subject of ongoing debate among cosmologists. Then there are the quasars, some of the most extreme and luminous objects the universe has ever produced. At the heart of every quasar sits a supermassive black hole actively devouring the gas, dust, and stellar debris swirling around it, generating a glowing accretion disk so bright that a single quasar can outshine every star in its host galaxy combined, sometimes by a factor of 1,000 or more. In 2013, astronomers identified a cluster of at least 73 quasars, stretching across roughly 4 billion light-years of space, a structure so large that a single beam of light would need nearly as long to cross it as our entire solar system has existed, and so massive that its estimated weight comes out to something on the order of 6 quintillion times the mass of our Sun. Quasars themselves also mark the frontier of how far back in time astronomers can actually see. For years, the record for the most distant known quasar was held by an object whose light left its source when the universe was only around 690 million years old, powered by a black hole already 800 million times heavier than our Sun, an object so improbably massive for its age that it strained existing theories of how black holes could grow so quickly. That record has since been broken more than once, and as recently as July of 2026, astronomers using the European Space Agency's Euclid Space Telescope announced the discovery of an even more distant quasar, catalogued as EUCL J1729, whose light set out when the universe was a mere 662 million years old, alongside a batch of 30 new quasars from that same impossibly early era, pushing the mystery of how the universe built such enormous black holes so quickly further back than ever before. Before Euclid began its survey, telescopes had only ever confirmed a handful of quasars from beyond the 770 million year mark, fewer than 10 in total across decades of searching. In its first 18 months of operation alone, Euclid more than tripled that number, transforming the study of the earliest black holes from a handful of isolated hard-won discoveries into something astronomers can finally begin studying as an actual population. All of these walls, voids, and superclusters are threads in what cosmologists now call the cosmic web, a vast sponge-like structure in which galaxies cluster along filaments and sheets, while enormous voids of near-total emptiness stretch out between them, containing so little matter that there are, on average, fewer particles inside them than in an ordinary empty room here on Earth. One of the most famous of these, the Boötes void, discovered back in 1981, spans roughly 330 million light-years and contains so few galaxies that early astronomers joked it could comfortably swallow our entire local group of galaxies more than 20 times over without brushing against a single occupant. Zoom out through every layer of that web, past the local group of galaxies that includes Andromeda and our own Milky Way, past Laniakea and its 100,000 galaxies, past the Virgo cluster and its 30,000 member galaxies, until you eventually reach the outermost boundary of everything currently observable, and you arrive back at the same unsettling anomaly this entire journey began with, the cold spot, sitting quietly in the direction of Eridanus, a scar that may or may not mark the place where our own bubble universe brushed against something else entirely. Nobody currently has a way to actually build a spacecraft capable of testing any of this directly. Reaching even the true edge of our observable universe using ordinary propulsion would take tens of billions of years, and by the time a hypothetical traveler arrived, the stars and galaxies visible today would have long since burned out, collided, or drifted far beyond any hope of return. Our own sun will exhaust its hydrogen and swell into a red giant, engulfing much of the inner solar system, roughly 5 billion years from now, and the Milky Way itself will have already merged with Andromeda into a single, unrecognizable galaxy well before that. Whatever lies beyond the cold spot, whether it turns out to be nothing more than a large, ordinary void or genuine evidence of a universe we can never directly visit, may simply remain permanently out of reach, a boundary we can measure, theorize about, and stare at from 93 billion light-years away, but never actually cross, at least not with any technology human beings currently have any real hope of building within our own lifetimes, or possibly ever. Slowly, relentlessly, that endless rain filled the basins of what would eventually become our oceans, carving out the low-lying regions of the crust and gradually submerging them beneath a growing global ocean. There's a genuine scientific theory that a substantial share of all the water currently sitting on Earth's surface ultimately traces its origin back to volcanic outgassing in those earliest chapters of the planet's history, meaning that without volcanoes, there may never have been enough surface water for life to have any chance of beginning in the first place. Some researchers also point to icy comets and water-rich asteroids as a contributing source during the same early period, but even accounting for that, most current models still treat volcanic outgassing as an essential piece of the puzzle rather than an optional one, since no combination of comet impacts alone appears sufficient to account for the total volume of water Earth's oceans actually contain today. Solid land came from a similarly violent process. Early Earth had no real continents, just a churning, mostly molten surface constantly bombarded by asteroids and comets, with no atmosphere yet in place to burn up incoming debris before impact, leaving the young planet exposed to a relentless barrage from space that only gradually tapered off over hundreds of millions of years. As the outermost layer finally began to cool and harden, the still boiling material underneath kept forcing its way upward through cracks and weak points, and over enormous stretches of time, that rising material built up in thick, buoyant layers that eventually became stable enough to persist. The very first true landmasses on our planet, small and scattered at first, more like isolated volcanic islands than anything resembling a modern continent. Even after Earth had its atmosphere and its first solid ground, volcanic eruptions never really stopped, continuing to reshape the emerging coastlines and mountain ranges for hundreds of millions of years afterward, gradually welding those early scattered land masses together into larger and larger formations as the planet's crust kept shifting and colliding above the slowly churning mantle beneath it. So we've got an atmosphere, we've got oceans, and we've got land. Now imagine, hypothetically, that volcanoes had simply switched off completely at that exact point, right after delivering those essentials, but before doing anything else. Even then, we still wouldn't be here, because the story of life itself appears to trace back to the same volcanic vents that helped build our oceans in the first place, an idea that has only gained more scientific support in the years since it was first seriously proposed by geologists studying the deep seafloor. In 2017, a team of researchers led by geochemist Matthew Dodd at University College London published findings from an extraordinary site in Quebec, Canada, called the Nuvvuagittuq Supercrustal Belt, home to some of the oldest rock formations ever discovered on Earth. Inside those rocks, the team identified microscopic tubes and filaments made of hematite, an iron-rich mineral bearing an unmistakable resemblance to the kind of structures produced by bacteria that still live around hydrothermal vents today. Based on the age of the surrounding rock, these fossilized microorganisms were dated to at least 3 billion, 770 million years old, and quite possibly as old as 4 billion, 280 million years, making them, if confirmed, the oldest known evidence of life ever found anywhere on the planet, predating the next oldest confirmed microfossils found separately in Western Australia by hundreds of millions of years. Hydrothermal vents, cracks in the ocean floor where mineral-rich, superheated water surges up from below, are widely considered one of the most promising candidate environments for where life on Earth may have actually originated, offering a steady source of heat, energy, and dissolved minerals in an era when the surface of the planet was still an unforgiving, radiation-battered place, long before the atmosphere had developed anything resembling a protective ozone layer. The tiny hematite structures the research team uncovered showed mineral compositions and shapes strikingly similar to modern iron-oxidizing bacteria that still cluster around vents on today's ocean floor, along with chemical signatures in the surrounding rock consistent with biological activity rather than any known non-living process. Without volcanic and hydrothermal activity on the seafloor, there may never have been anywhere hospitable enough for that first spark of biology to take hold at all. Every living thing on Earth today, humans very much included, may ultimately trace its lineage back to microorganisms clustered around volcanic vents on the ocean floor nearly 4 billion years ago. An almost dizzying thought the next time you happen to walk past an active volcano, or even just an ordinary hot spring anywhere in the world, on any continent, on any given day. All right, so volcanoes gave us air, water, land, and quite possibly life itself. Surely, once all of that is in place, we could switch them off for good with no real consequences. Except, once again, the honest answer is no. And the reason has everything to do with what's constantly happening deep beneath our feet, whether we notice it or not. For a long stretch of Earth's ancient history, the planet's land masses were fused together into a single enormous supercontinent geologists call Pangaea, surrounded by one continuous global ocean, a configuration that persisted for tens of millions of years before it finally began to break apart. Beneath that supercontinent, heat continued building up inside the planet the entire time. Earth's interior is layered like a nested set of shells, a solid inner core hotter than the surface of the sun, a molten outer core churning with liquid iron and nickel, a slowly churning layer of superheated rock called the mantle that moves in what scientists call convection currents, rising, cooling, and sinking again, in a cycle that has continued uninterrupted for billions of years. And finally, the relatively thin, brittle crust we actually live on, broken apart into massive interlocking plates that are perpetually, if imperceptibly, sliding around on top of that circulating mantle beneath them, moving at roughly the same speed a human fingernail grows. It was that same underlying process, plate tectonics, that eventually tore Pangaea apart into the separate continents we recognize on a map today, a process that unfolded across tens of millions of years. Far too slow for any single observer to have ever perceived it happening, even though it never actually stopped, and continues reshaping the arrangement of Earth's continents to this very day, millimeter by millimeter, year after year. Every time those plates grind against each other, they generate earthquakes, and in some cases, they generate volcanoes as well, and both of those processes are essential to how our planet continually renews itself. Where two plates pull apart from one another, fresh magma wells up to fill the gap, creating brand new oceanic crust in a process happening right now along mid-ocean ridges that stretch for tens of thousands of miles beneath the world's oceans, mostly invisible to anyone who has never actually seen a map of the seafloor. Where plates instead collide or slide beneath one another, that same tectonic pressure can force one slab of crust deep back down into the mantle to be recycled, or thrust mountain ranges skyward as the colliding rock has nowhere left to go but up. The Himalayas themselves, a direct, ongoing product of that exact process, still slowly rising to this day as the Indian and Eurasian plates continue their extremely slow motion collision.